Hi everybody, this is Mr. Folly, and welcome to podcast 2.3, where we will explain the trends of the periodic table. All trends are due to size, nuclear attraction, and maybe shielding. Okay, that you need to know that. All trends are due to size, nuclear attraction, and shielding. Electronegativity, you need to know the definition, the equation, and the trend. Ionic radius, you need to know the definition, the trend. Ionization energy, you need to know the definition, you need to know the trend. And you have to learn the exceptions that come through. So let's hop to it. Explain the main way atoms differ, and he just explained every trend. So the way they're different is size. Bigger is less attractive. High school romances don't last through college. So what this means is, it means stop changing on me. If you go to school over here, let's say you go to the wonderful school of University of Chicago, because we know that's close, and your little Chicago, and your little Snookums decides to go to LSU, go Tigers. Notice that's very far away. If they're very far away, what happens is your little Snookums will find other people that are probably just as attractive as you, but a little bit better because they're closer, right? Proximity, location, location, location. So while you might be perfect for each other, someone almost as perfect might actually just be a little bit closer. Aww. Okay. So the bigger you are, bigger is less attractive because the attraction weakens with distance. Nuclear attractions. More protons means more attraction. Okay? More protons means more attraction. Shielding. Inner electrons make a nucleus less attractive by blocking the attraction. So let's pretend I have a nucleus right here. And it's pretty darn positive. Look at all those positives in there. Okay, and if you're an electron over here and you're like, hey, I like you, nucleus. The nucleus is like, hey, I like you, electron. But what happens is you have a layer of electrons right here. This would be like a bunch of big scary family members that say, stay away from my sister, brother, whatever it is, child. Okay, so these electrons all push away. So these guys all repel this electron. Okay, inner electrons make a nucleus less attractive by blocking the attraction. Okay, so if you can say these three things, you can talk about the size of the atom, you can talk about the number of protons, and you can talk about shielding. Now shielding is only an upsy-downsy trend, okay? Because if I have one layer or if I have another layer, wouldn't two layers of shielding make it even more repulsive or less attractive would be the case, okay? Electronegativity, which you saw for a fraction of a second. Ability to attract electrons in a bond. So what happens is I'm atom number 1, hi atom, and I'm atom number 2, hi atom, and they have electrons, 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 and they're bonded. And what happens is, oh, I forgot, I can't easily erase. What happens is, if atom number 1 is more attractive, all the electrons are over here, most of the time. Whee! And they just spend a little bit of time over here. Aww. That's sad. The trend fluorine is the Mac Daddy. That means you're the best. Francium is a big loser. So notice fluorine, if I draw my periodic table, here's fluorine. I'm sorry, here's francium. This is francium. Here's fluorine. Fluorine is the best. Francium is the worst. Okay? Fluorine is the Mac Daddy. Now, why would it be the Mac Daddy? Okay? Fluorine is small. Hey, that's size. Fluorine is attractive because it has so many protons for its row. Hey, size, nuclear attraction, so be able to attract bonded electrons easily. So if you're close by and attractive, you attract electrons. So be able to attract bonded electrons easily. Notice how I've redefined the trend in that. So why is francium so bad at this? francium is big, has the fewest protons for its row, so it isn't very attractive. So it attracts bonded electrons poorly. I think you were clicking 2 slides at once. Ionic radius, this is the size of the ions. Okay, ionic, ion means positive or negative. Cations get smaller. Why? So let's take a look at this. If I'm a nucleus and my cations have, say, I've got 2 electrons in my outer row. And what happens is I lose 2. Here's my nucleus. And then look, let's say I have 2 in here. My outer ring now has 2. Notice how this used to be 80 big, and this would be 20. And now it's only 20 big. Why? You lose an entire energy level. Okay? Anions get bigger. Why? Okay, so let's pretend I'm an anion. Here's my positive 1. Here's my 2. And let's say I have 6 electrons. If you recall, 8 is what makes you full. Let's change the slide for no reason. So if I have 8 electrons, what happens is I start off with, if I add an electron here and add an electron here, won't they repel each other because they're like charges and spread out even more? So what happens is the extra, let's change the slide for no reason again. Extra electrons repel and push valence electrons away, making it bigger. I'm sorry, it took me 3 tries to write the word repel. Ionization energy. Definition. Energy to remove 1 electron from the valence shell of a gaseous atom. Ionization energy is remove 1. Hey, that makes you a +1 ion. Okay? Unless you're already a +1, then it can make you +2. Hey, I like when it changed slides for no reason. Fluorine is the Mac Daddy. Francium is a big loser. Why is fluorine the best? Fluorine is small and attractive because it has so many protons for its row, so it takes more energy to remove an electron. Please stop changing. Okay? It takes more energy to remove an electron. Okay? So if you're trying to remove it, then being small and attractive is helpful. Second and third ionization energies are possible, which means you can remove a second electron and a third electron. If you remove a second electron, you become, changing the slide for no reason, +2 and +3. Okay? Now, francium is bad at it because if you want to remove an electron, if you want that energy to be low, if it's a big loser, it takes little energy to remove an electron if it is weakly attracted and far away. Remember, far away makes the attraction even less. Okay. So if we look at it graphically, look, hydrogen, helium, it goes up. And over here the general trend is it goes up. Over here the general trend is it goes up. Okay? Now there's a couple of little hiccups here. And those couple little hiccups we will discuss in class. Okay? So now ionization energies can be used to predict the family. If you leave the full, stable, small and attractive noble gas state, it requires a huge change in energy. So let me show you what happens here. So notice well, that's not what I'm looking at. Let's go here. So this change is about 500. This is about 5,000. This is about 7,000. This is about 9,500. This is about 13,000. This is about 16,000. This is about 20,000. This is about 25,000. This is about 29,000. And this is about 141,000. Whoops. Do you notice we have a change of a power of 10, right? About 10 times bigger. What that means is on the second column, that is where we left the noble gas state. Left noble gas. Okay? So what that means, if I'm looking at a periodic table, remember these guys have one valence electron. These guys have two. We don't worry about valence electrons in the D block at all. 3, 4, 5, 6, 7, 8. Okay? So if I have one valence electron, the first time I lose it, I end up here. Oh, come on. I end up here. So this first one was easy. Why was it easy? Because I landed on the noble gas. As I left here, it would be huge. So wherever that huge one is, that means the second one would be huge. Okay? So let's look at a new one. If I had tiny, so let's say I had small, small, huge. So if I have small, small, huge, I hope you wrote that down because when I write it, it disappears. So that means if my first one was small, and my second one, if this is my huge one, right? So if the third one is huge, and that was my third, my second one would be small, and my first one would be small. So that means that this would indicate it's the alkaline earth metals. And we'll do more with those in class. Reactivity. Metals react by losing electrons. Francium is big and unattractive, so it's the best reactive metal because it is the best loser. Nonmetals react by gaining electrons. Fluorine is small and attractive, so it is the best reacting nonmetal because it is the best gainer. Okay? So if I look at trends in the periodic table, if I'm doing a metal, the most reactive metals go this way. But the most reactive nonmetals, let's see if I can change my pen to a different color. Most reactive nonmetals go this way. So if I were to ask you what's more reactive, scandium or calcium, you would say calcium because it is bigger. That's not bigger. Shoot. Calcium because it is smaller, thus more attractive. Oh, I did that wrong again. I can remember this. Calcium is bigger. My bad. Oh, give me a pen. I'd like to say this continual part. Calcium, see how calcium is on this side, it has fewer protons. It's bigger and less attractive. So it is a better loser. Okay? So, come on now. So calcium is more reactive. Now if I were to compare sulfur and selenium, two nonmetals, sulfur is smaller, thus more attractive. So it gains electrons and reacts better. Okay? So, you should know what ionization energy is and its abbreviation. Electron affinity, we've dropped. Electronegativity, ionic radius, all have definitions you must memorize. Ionization has exceptions that you don't need to know yet. We'll cover that later. Size, nuclear attraction, shielding explains it all. Fluorine is the best. I'm glad it's decided fluorine is the best. Francium is the worst. But fluorine is not the Mac Daddy of size. That is it. Let's say toodles. And let's get out of here. Out of here. Toodles.